Welcome back, protein coders. Let's build some coding muscles. Today we're gonna see Floyd-Warshall algorithm. It is a multi-source shortest path algorithm, which means for every node we have to find shortest path to every other node. Okay. So for A we have to find shortest path from A to A, A to B, A to C, A to D. Similarly for B, C, D also. Okay. We will have a matrix for this. So in the graph given we have an edge from A to B, which is at a distance 10, right? But see, if we go from A to C and then C to B, we will get a distance of 2 plus 5, which is 7, right? If there is edge from A to C and then C to B, we can say we have edge from A to B, right? Then we will update the shortest distance to 7. Now if you see, if you go from A to C, C to D, and then D to B, right? So A to C, then from C to D, and then from D to B. So we can say that we have edge from A to D, right? And then similarly from A to D and then D to B, that means we can go from A to B. And this time our path weight will be 2 plus 1 plus 2, which is 5. So we got the shortest path here. So this associative nature of our algorithm, this associative property which we are using, it's the contribution of the Warshall, okay? And the updation which we are doing for the shortest path is the contribution of Floyd. So what the algorithm does is, suppose we have, let's pick a node A and we have all other nodes A, B, C, D. So we will take an intermediate node, okay, let's say A, and we will find the shortest distance to all other nodes. Then what we will do, we will take another intermediate node, let's say B, and we will find all the other shortest nodes, and we'll repeat this process. So what we are doing is, for every node A, B, C, D, right, and what we are doing is we are picking an intermediate node and finding the shortest path. Okay, we are relaxing the edges for every intermediate node, right? So for every intermediate node, we will relax edges using associative property. So if I write in equation, it will be if distance of A to B, okay, is greater than distance of A to C and distance of C to B, which here I am taking C as an intermediate node, then I will relax this edge, okay, and this I will do it for every node, right? And for every, and this whole process I will do it for every intermediate node. So I will pick an intermediate node and I will find the shortest path between all the edges to all the edges, okay, via this intermediate node. So let's see in the code how we're gonna do it. First we will run a loop k from 0 to n, and this is the intermediate node, okay. This loop is for intermediate node, for choosing intermediate node, okay. Then we will run another loop for I equals to 0 to n and j equals to 0 to n. So if you see in the graph, what is this is, we are choosing I, right, from 0 to n and j from 0 to n, and for every I and j we are picking a intermediate node, okay. So now we will relax the edge. If distance of ij is greater than the distance of I to k and then k to j, then we will relax it, okay. If you find another path which is shorter than this, then we will relax the edge, and that's it. That's simple it is. That's how our Floyd-Warshall ends. Okay, congratulations. Now if you see the time complexity, we are running 3 for loops, so it will be order of p cube. Okay, now let's revise first what we have studied. Floyd-Warshall, we are using associative property that if there is a path from A to C then C to B, right, then we can reach from A to B, okay. And we are exploiting this property. We are choosing an intermediate node, and for every intermediate node we are relaxing edges from every node to every other node, okay. And then we saw the code for this, and in code we saw we run a loop to choose the intermediate node from that is k 0 to n, and then we'll choose I and j and we'll relax the edge. The distance of I and j is greater than ik plus kj, okay. Now one more thing I want to discuss with you guys. So let's say at the end we get this final shortest distance matrix, and we will have the diagonal elements to be 0, right? Distance of A to A will be 0, B to B will be 0, C to C will be 0, D to D will be 0, right? The Floyd-Warshall also works with the negative weights. Okay, if there are negative weights present, then we can use Floyd-Warshall, but it can also detect the negative cycles. So let's say we have a graph here. Okay, see, it's a negative cycle, right? We can reach from A to A and it will get us -1. If we again do this, we will get -2, right? So if such case happens, one of the diagonal elements of the shortest distance matrix will be negative. Okay, so from there we can detect if there is a negative cycle present or not. One another thing, let's say we have positive weights in our graph. Then what? Can we use Dijkstra? Let's say our graph is sparse. So the Dijkstra for single node will be E log V, right? And for every node, if you run this, this will be VE log V, right? Which is better than VQ, which is better than Floyd-Warshall. Okay. And if we have dense graph, then the Dijkstra complexity will be order of V square. If we do V times, it will be V cube. So similar to Floyd-Warshall. And in Floyd-Warshall, we can detect cycles, negative cycles also. It works with negative edges also. So it's better in that case. Okay. So that's all from my side, guys. If you have any questions, please mention them into comment box. You can find problem solution link into the description box. If you don't understand, don't like, don't subscribe. But if you do, please show some support. Keep smiling, keep practicing. Thank you.